In this video, I will explain you how refraction will occur through a curved surface. So far we have learned the refraction occurring through a plane surface, that a ray would come, this we call it incident ray, and that would go refraction, that is change in direction with respect to incident ray in a different media. So this can be better explained with a normal drawn. So with respect to normal, incident ray makes an angle of I, and if this is a denser medium, then the refracted ray makes an angle R, and I could say that R is less than I in the case of a ray entering from rarer medium to denser medium. So whenever the ray is being entered to a denser medium, then the refracted ray would go towards the normal. Clear? So this is the case. Now when the same process, that is process of refraction occurring on a curved surface, it's the same thing, the same process, same equation we can apply here, that is nothing but Snell's law, where sin I by sin R is equal to mu2 divided by mu1, where mu2 is the refractive index of second medium where the refraction has occurred. So the refracted ray is in the second medium, this is in the first medium. So this is incident ray. Okay, incident ray meet the curved surface, and after that undergoes refraction, and the refracted ray is now in medium 2, that is in the denser medium. So this law can be applied anywhere, whether it is plane surface or curved surface. But in the case of curved surface, we are taking some approximations. Okay, so first I will explain you how this process is happening. We have a rarer medium, so this can be air or free space. So from here an incident ray is going in this direction. Okay, this one is my incident ray. Now this is my denser medium. Okay, M2 is my denser medium and this is my rarer medium. Now from rarer medium, light ray is entered to denser medium, and here refraction is occurring because the whole thing, see, this part is medium 1 and this part is medium 2. So you can say the whole part from here it is made up of glass, and here it is just air. So rarer medium and denser medium, light ray enters from rarer to denser medium. Okay, so how to get the refracted ray at this position? Just draw a line that is nothing but normal to the surface where the incident ray met the curved surface. Okay, now when this is circular in nature, all the normal when we are drawing at any point, I am drawing a normal here and here and here, any normal drawn at any point would pass through the center of the curved surface. So this is the center of the curved surface, and this ray, this normal would be simply the radius. So here, from here to here, if you are drawing the normal, it's radius. So always keep in mind that whenever you are drawing a normal in a curved surface, that would go through the center of the curvature. So here, this is my normal. So with respect to normal, incident ray is making an angle of I. Now refraction would occur and refracted ray would go in this direction, and the refracted ray, this ray is making an angle R here. So this is incident angle and this is refracted angle. Okay, now this one, the normal is simply my radius. Okay, yes. Now first thing is an approximation. This can be done anywhere, not only in ray optics or wave optics. That is, for small angle I, for small angle I, sin I is equal to I is equal to tan I. You can replace sin I as I, you can replace I as sin I, you can also replace I as tan I, you can also replace tan I as I. So any interchanging, any kind of interchanging is possible in between these three terms. These three are equal only for a small angle. Okay, so this is what we are doing in addition when we are considering a curved surface. Okay, now this is my incident ray, right? And this is nothing but a line which is passing through the optic center. So this one is my optic center, and a line is passing through optic center, and that is also passing through my center of the curvature. So this line, so this is okay. Now to get an image, I need two rays, right? So one ray is going in this direction and another ray is going in this direction, from O to M, then from M to I. Okay, so this is one of my ray from the point object, and this is my next ray. These two rays is being intersect at this position, so an image is formed here. So object is here, an image is formed. For an image we need two rays. One ray is this and another ray is this. So this is how we will get the image of a point object. So we will take one ray as this one itself and the second ray as a refracted ray. For this ray there won't be any kind of refraction. What is the reason? This ray is going along the normal. So if in a process of refraction, if incident ray is along the normal, after refraction that doesn't change its direction. Okay, so I have told you we can apply this equation here, Snell's law. So as per Snell's law, I can say sin I by sin R is equal to mu2 divided by mu1. So mu2 is nothing but the second medium, refractive index of second medium. Mu1 is nothing but refractive index of first medium. Okay, so here in mu2 we have the refracted ray, in mu1 we have the incident ray. Okay, this is how you can learn it. Now we need angle I and R, right? Now incident ray is making an angle. So this is my one of the ray, and this ray is passing through my optic center and center of the curvature. Now with respect to this, the principal axis, this is my principal axis. With respect to the principal axis, the angle made by incident ray is alpha. Okay, with respect to principal axis, angle made by incident ray is alpha. With respect to refracted ray, the angle made by principal axis is beta. So this is principal axis, refracted ray, angle made is beta. Now with respect to the radius, angle made by principal axis is gamma. So incident ray and principal axis alpha, refracted ray and principal axis beta, radius and principal axis gamma. These three are very important angles. Now angle of incidence and angle of refraction as per we have learned previously. Okay, we need I and R. So how to get the angle I and R? Just consider this triangle, the triangle from triangle OCP. I is an external angle, right? And alpha and gamma are internal angle. So I can say that from triangle OCP, angle I is equal to angle alpha plus angle gamma. Exterior angle is equal to sum of interior angle. Now from triangle CIP, we will get a new relation, CIP. This is my exterior angle and that is equal to sum of interior angle. So what is exterior angle? Gamma. So angle gamma is equal to interior angle R plus angle beta. We need I and R here. So I also have told sin I can be replaced as I. So here on doing this kind of approximation, this approximation is done here, where I can say sin I is equal to I and sin R is equal to R. So I by R is equal to mu2 divided by mu1, or mu1 into I is equal to mu2 into R. Okay. Now for I have a value here. I is equal to mu1 into, what is I? Alpha plus gamma is equal to, what is R? Mu2 into R is nothing but angle R from here is angle gamma minus angle beta. Bring beta here. So angle gamma minus angle beta. Okay, now multiply, cross multiply. Mu1 into alpha plus mu1 into gamma is equal to angle gamma and angle beta. I'm just going to take it as gamma and beta. Okay, just eliminate this, else we will have 3 terms in the equation. Okay, so mu2 into gamma minus mu2 into beta. Bring gamma terms together and beta, the other terms to the other side. So mu1 into alpha, this will become mu2 into beta is equal to mu2 into gamma minus mu1 into gamma. From here, bring gamma as a common term into mu2 minus mu1. Okay? Yes. Now, again I can do approximation. I can be taken as tan I. So here, alpha can be taken as tan alpha. So from here, we are continuing. Okay. Mu1 into alpha is tan alpha plus mu2 into beta is tan beta is equal to gamma is tan gamma. Now mu2 minus mu1. Now what is tan alpha? From this triangle, opposite by adjacent. So mu1 into opposite is PM divided by adjacent is OM plus mu2 into, this is mu1, mu2 into what is tan beta? This is beta, tan beta is PM divided by opposite by adjacent, MI. This is equal to what is tan gamma? Opposite by adjacent, PM divided by MC. So PM divided by MC into mu2 minus mu1. Now PM is a common term here, so I can cancel out from all the terms. So mu1 divided by, what is OM? OM is the object distance and that is measured in this direction. All rightward directions are positive, leftward measurements are negative. So this is a leftward measurement. OM is the object distance minus U. Okay, minus U. Plus mu2 into what is MI? MI is the image distance, that is measured in this direction, rightward length it is. So that is plus V is equal to 1 by, what is MC? MC is measured in this direction and that is radius of the curvature, radius it is. So 1 by plus R into mu2 minus mu1. So this says that, rearrange it, mu2 divided by V minus mu1 divided by U is equal to mu2 minus mu1 divided by R. This is a very important relation. Now this equation can be applied when the light ray enters from rarer medium to denser medium through a spherical surface. So this spherical surface can also be a concave surface. Now for convex surface it is true. For convex, from rarer to denser medium, when the light ray is entering, when the refraction is occurring, I can apply this equation because we have derived it. Refractive index of second medium divided by object, see, in the second medium, sorry, divided by image distance. Okay, so in the second medium is the image here, V is in the second medium. So refractive index of second medium divided by image length minus refractive index of first medium. Now here is my object, so divided by object distance is equal to mu2 minus mu1, that is the difference in the refractive index of second medium with respect to first medium divided by radius of the curvature. Now whenever you are doing numericals, you have to substitute V and U and R with the appropriate sign. Okay, now this can even be applied when the curved surface which we are going to consider is concave in nature. This is convex in nature. Now for concave also that will hold true. In the next video, we will take an example where light ray is entering from a denser to a rarer medium in the case of convex lens. Okay, thank you.